today go to a physical topic, an important application of complex analysis which has to do with response of physical systems. So, we will do a little bit of linear response, we will see where complex analysis helps. Okay. So, I will start with the description of a general physical problem, and then we will specialize to the case of dispersion relations. We will derive dispersion relations after defining a response function appropriately. Okay. What I have in mind is part of a very large number of physical systems where you disturb the system by some stimulus and the system responds in some manner which you measure and so on. And roughly speaking, one expects the greater the stimulus, the greater the response. This is an example of linear response, and there are lots and lots of physical systems which, at least for small values, suitably small values of the stimulus, would respond in this linear fashion. For example, Ohm's law. You apply a voltage and the response of the system is a current, and the current is proportional to the voltage by Ohm's law. Similarly, Hooke's law. You apply a stress on a system, and in the elastic region the strain is proportional to the stress, to the first power of the stress. Similarly, you apply an electric field on a dielectric, and as long as you do not go to the region of dielectric breakdown and so on, as soon as you apply a small electric field, there is a small dielectric polarization of this medium, which is the response. Okay. You apply a magnetic field on a magnetic system and it responds by acquiring a magnetization, like in a paramagnet, for instance. These are all examples of linear response, every one of these things, and there is a very elaborate theory of this linear response. What we would like to talk about is the fact that if you apply a stimulus on the system, the response also depends on whether this stimulus has one kind of time behavior or another. For instance, if it is an oscillatory stimulus, like an oscillating voltage applied to a circuit, electrical circuit like an LCR circuit, the response could be quite different from what happens if you apply a DC voltage to the system, right. So, as you know, physical systems would respond in a manner which depends on the time dependence of the stimulus that you apply to the system. Now, the most general thing you could do is to take an arbitrarily time dependent stimulus and ask what is the response to, and that problem is most easily analyzed by saying I will first take this stimulus, break it up into frequency components by a Fourier analysis, and then for each Fourier component I will ask what is the response of the system and superpose all these, simply because it is still in the regime of linear response. So, that would be a logical thing to do. Now, let us try and write down what the most general response for a system could be, making certain basic physical assumptions, namely the linearity is most important, and I will put in a couple of other physical ingredients which, when you relax, you get more general kinds of response, but this is the simplest system, the situation that you can have. So, I am going to call the response of the system some R of t, and the stimulus or the force that I apply on the system, I will call it F of t, some general force. So, this is response, and I am going to relate it to the force that I apply on the system or the stimulus in a certain specific manner. Okay. If this stimulus is F of t, this is the stimulus or force, it is also time dependent. The question is, how does this depend on that? If it is linear, it can at best be some linear function of this F of t, but of course a force applied over a period of time, the response would start after you start applying the force. So, certainly there is causality in that sense. You do not want the cause to precede, the effect to precede the cause. You also want it to be linear. So, the most general thing you could possibly write down is some kind of superposition of the following kind. So, it would be an integral in the general case, it could be a sum, but it could be an integral if there is a continuous application of the stimulus from the earliest time you can imagine, which is minus infinity, dt prime, and then there is an F of t prime. So, it is a superposition of all the forces that you apply multiplied by something here which is the response per unit force, and that is the reason you are multiplying the whole thing by f of t. So that response per unit force, let me call it some phi, which will depend on the time at which you applied the force as well as the time at which you measure the response. Okay. And the question is, where does this integral cut off? It cannot go on to plus infinity, because today's response cannot depend on the force which is going to be applied tomorrow, right. So clearly it is going to cut off at t itself. It can't possibly be anticipatory. So this is causality. Causal response. So that cuts the integral off here, and that is very important. You can see. The fact that it is linear in f, this function does not depend on f, it is the response per unit function. So this shows linearity, linear response. Okay. And there is one more ingredient we are going to put in for physical reasons, and that is to say, look, it does not really matter if the system is not changing its underlying properties, inherent properties as a function of time. It does not really matter whether I do the experiment today or tomorrow or any time. All that matters is the time difference or the time interval between the time you apply the force and the time you measure the response. The absolute time does not matter at all, provided the system is not changing or aging. For instance, if you measure the elastic modulus of a piece of steel, if the steel does not undergo any structural changes in between, then whether you do this experiment today or tomorrow and so on will not matter. On the other hand, if you did the same thing with that flyover outside, the concrete bridge, that ages, concrete ages, and therefore its elastic behavior changes with time. And then indeed this phi of t is a function of t and t prime in this fashion. But if you do not allow for this kind of aging, if you say this system is independent of the origin of time, then this response can only depend on the time elapsed since the application of the force. So it is a function of t minus t prime alone, okay. Some kind of retarded response. Okay. So this implies retarded response. Every one of these assumptions can be relaxed depending on the situation, and then you get something totally different, but we are going to stick to this. So we are going to look only at cases of causal retarded linear response, and then this is the most general thing that you can write down possibly. Okay. Now of course you could also argue saying that, oh, this force is a vector in general in mechanical cases. It could be an electric field, it could be a stress, in which case it is a tensor of rank 2, and the response would also have a similar character, right. That is true, that is certainly true. So this could have many components, that could then have many components as well, and this response function in between would connect this to that, and that would also have a large number of components. For instance, if you took an electric field and you applied an electric field here, it has 3 components in 3-dimensional space. This thing here is the polarization, which is also a vector, has 3 components, and the most general way of linear relationship between a vector here and a vector here is through a second order tensor here. So you would have a 9 component object here, you would put in indices here in all these places and so on. So for simplicity, let us get rid of those things right now, just write it as scalars for the moment, but we can put in all the indices that you like. For instance, if this were a stress tensor, it would have 9 components, symmetric rank 2 tensor in 3 dimensions. This would then be a strain tensor, it would also have 9 components here, and this thing here is the compliance tensor, and that would actually have 81 components. It would be a rank 4 tensor. But of course we know that there could be symmetries in the system and so on, and then this number 81 is reduced. You do not have 81 elastic moduli for anything, you have a much smaller number, and if the material is for instance cubic crystal or something like that, there would be a small number, hexagonal crystal has some 6 or some such thing, and a cubic crystal for example would have simple cubic, just to take simple example would have shear modulus, and then it would have a longitudinal modulus and a transverse modulus. If it is an isotropic medium, it just has two independent elastic constants, which you could choose to be, say, the bulk modulus and Poisson's ratio, or you could choose them to be the Young's modulus and the shear modulus, for instance, and so on. But we are not interested at the moment in these indices. This is the general framework in which things are going to be measured, and this we are going to discuss it in this framework. This is called the response function. Now, what do you expect of this phi physically? What would one expect? Well, let us stick for the moment to real functions here and real functions here. So, there is a real physical force and a real stimulus, and this thing is a real connector between the two, response function. Now, what we expect of this is, if I plot, let us call t minus t prime equal to tau, say, if I plot tau as a function, phi of tau as a function of tau, then I expect that if the force is fresh, I expect a high response, and then as the time delay increases, the response due to this force decreases as time goes on. So, in general, I would expect that this phi of tau would start at some point and maybe decay exponentially, or otherwise it would decay in some fashion. It could also oscillate. There is nothing to stop it from oscillating. It could become negative at some times, it could become positive, we do not care. So, all these scenarios are permitted, could do that, could do any of these things. What I do not expect it to do is to increase as a function of time. In general, you do not expect that. You expect the effect of what happened day before yesterday on you today would certainly be less than the effect of what happened yesterday and what is happening today. So, I would expect this to be some kind of decaying function of tau. Could go to 0, could go to a constant, we do not know at the moment, we do not care. Okay. Now, given this, what can we say next? Well, the most general form of r of t that you can write down would be equal to, do a Fourier transform, so minus infinity to infinity d omega e to the minus I omega t r tilde of omega. R tilde of omega is the amplitude of this response at time t corresponding to the frequency omega. I am going to use omega for the frequency. I guess you are familiar with it as angular frequency, but I will just call it the frequency. Okay. And I have chosen a particular Fourier transform convention. There are as many Fourier transform conventions as there are people, but I will choose one and stick to it in this fashion. I chose minus here, so this will of course imply that r tilde of omega equal to integral minus infinity to infinity dt e to the plus I omega t, that is for sure, and this is minus, that is plus, and then r of t, and we have to be careful because the delta function has a 1 over 2 pi, so I will put as a 2 pi, so I put the 1 over 2 pi here. Okay. Is this okay?
Put the square root, so I don't have
Is this okay? Now there are people who put a square root of 2 pi here and a square root of 2 pi here, but these are the sort of people who also write j for I. So, since they are beyond the reach of humanity, I will write I. Right. You still write j? You still write j? Engineers write j, electrical engineers write j, right? They do this. Probably very sensible because they use I for something else, right? For current. But physicists like to use capital I for current. The reason being that it can then be confused with intensity, and physicists like to have confusing notation, right? But I stick to this. I stick to this, I think here. I guess they also write 2 pi nu out here. I don't like to put too many 2 pi's in the exponent and so on, so we just call it omega there. That's the inverse Fourier transform there. Okay. Then you could do the same thing with the force, and therefore f of t equal to integral d omega e to the minus I omega t f tilde of omega. That implies and is implied by f tilde of omega equal to 1 over 2 pi dt t f of t. Okay. Now we plug that into this. So let us put that this Fourier representations into this and look at what happens. So on this side, if I Fourier transform this, I get an integral minus infinity to infinity d omega e to the power plus I omega t, or minus I omega t, r tilde of omega equal to, on the other side, minus infinity to infinity dt prime phi of t minus t prime integral minus infinity to infinity d omega e to the minus I omega t prime, that is important, t prime f tilde of omega. All I did was to write the Fourier representation for each of these functions of time, and then I interchange order of integration. Okay. Provided these things converge fast enough, uniformly enough, and so on, you can interchange the order of integration. If I do that, pardon me, is it where f of t prime
minus infinity to t.
Absolutely, yeah, minus infinity to t, that is very important. Thank you. So this becomes equal to integral minus infinity to infinity d omega f tilde of omega. I can't pull out the t prime outside because it's still got to be integrated over. So minus infinity up to t dt prime phi of t minus t prime e to the power minus I omega t prime. This fashion. But let us write that, let us change variables. Let us change variables to t minus t prime. So let us put that, I have already said that here, t minus t prime is tau, say, and it is the t prime, that is the variable of integration. So dt prime equal to minus d tau, and this becomes equal to integral minus infinity to infinity d omega f tilde of omega, and integral when t prime is minus infinity, tau is infinite, and when t prime is t, tau is 0, but there is a minus sign here in the Jacobian. So this is equal to 0 to infinity d tau phi of tau, and then e to the minus I omega t prime, which is e to the minus I omega t minus tau. Okay. And of course you can pull this out here, so this integral becomes equal to integral minus infinity to infinity d omega e to the minus I omega t f tilde of omega times e to the plus I omega tau on this side. So that is what this thing becomes equal to on this side. Now let us collect the terms together and look at what happens. So we find integral minus infinity to infinity d omega e to the minus I omega t times r tilde of omega minus, I bring that to this side, minus an integral from 0 to infinity d tau e to the I omega tau phi of tau. That is a function of omega because the tau has been integrated over. It is a function of omega multiplied by f tilde of omega, and the whole thing is equal to 0 on this side. Okay. Now I argue as follows. This thing here, as omega runs from minus infinity to infinity, forms a complete set of functions, orthonormal set of functions of t. That is why you can do a Fourier transform, right. So when two Fourier transforms are equal to each other, the functions are equal to each other, because if two Fourier transforms are equal to each other at each frequency, This implies because e to the minus I omega t is a complete orthonormal set of functions of t in minus infinity to infinity, it says that the coefficients are equal. So the Fourier transform of 0 is 0. Therefore, it implies that coefficient by coefficient this must be equal to 0. Otherwise you can't superpose all of them to get 0. So that is how you normally do Fourier transforms and equate the coefficients, and the reason of course is that you are equating the components of a vector and function space of the individual components in a basis, a certain orthonormal basis. So this implies immediately that this is equal to that for each omega, for each real omega. And this is some function of omega. So let us call that, give it a name, chi of omega, f tilde of omega, and this chi of omega is called the generalized susceptibility. It is a frequency dependent susceptibility. Now what is it telling you? It is telling you that if you put this thing here, you recall naively when you are in high school you learned that a relation like the magnetization is proportional to the magnetic field and m divided by h is equal to the susceptibility chi, right. What you are really saying is that the magnetization per unit applied force, per unit magnetic field is your susceptibility, and now accept that the unit is in the frequency. So at each frequency per unit amplitude, this chi of omega measures the corresponding response at that frequency out here. So this is what the dynamic susceptibility or generalized susceptibility does. Okay. And how is it related to the response function? It is given by this. So that is very, very crucial, that relationship. It says chi of omega is equal to an integral from 0 to infinity it is the integral of the response function, it is a definite integral, so I might as well call it dt e to the I omega t phi of t. Remember that this function is defined only for positive values of its argument, because that really came from phi of t minus t prime. It is a response function. It starts at t equal to 0 and then it continues forever beyond that. So that function is defined only from 0 to infinity in its argument, and indeed this susceptibility also involves the integral only in that range. And this happened, why did this happen? Why did this get cut off at 0? What? Causality. Because that 0 came from the limit t in the response, causal response, when I change variables, and that got cut off at t rather than plus infinity because of causality. So this is responsible, this thing here is an effect of causality. Is this a Fourier transform? Is it a Fourier transform of the response function? No, because the Fourier transform would be minus infinity to infinity. This function is not even defined in the negative. I could define it by continuation or anything, and then of course I would have to specify what sort of phi of t I am talking about. We will come to that, I will try to point out later on where this phi of t actually comes from. In the theory of linear response, this phi of t will turn out to be a certain correlation function which will have a meaning even for t less than 0 depending on the time reversal properties of the operators concerned. Okay. So at the moment we do not know that, this is it. This is not a Laplace transform because that would be e to the minus st. This is I omega. So it is neither a Fourier nor a Laplace transform, so we call it a Fourier Laplace transform, a one-sided Fourier transform of this. But it is going to create certain problems because of this, because if it were a Laplace transform you could define it even if this function went to a constant at infinity, but now that is going to be problematic here. Okay, So let us look at this response function and see where it takes us. First I am going to assume, this is an important assumption, that the way we have looked at this, I am going to assume that this integral actually exists, that it is finite. It is a Fourier Laplace transform, so we have to be a little careful about this. The generalized susceptibility is the Fourier Laplace transform of the response function, okay, that much we know, and we are going to assume that it exists for real values of omega. In particular, we are going to assume that it exists for 0 frequency, namely a DC force. This is an assumption and can be relaxed, we can settle it, but right now let us assume that everything is okay, this integral exists, and we go ahead with it. What can we say about it immediately? The first thing we realize is that this is a complex number, because it has got a real part and an imaginary part. If phi of t is real, there is a sine part and a cosine part, and it follows immediately from this, the fact that you have a sine here and a cosine there, for the real and imaginary parts you have cosine and sine respectively. This immediately implies that the real part of chi of minus omega equal to real part of chi of omega. In other words, the real part is a symmetric function of omega because it involves cos omega t, and the imaginary part is an odd function for real omega. At the moment omega is real. This symmetry is going to be very, very important. Okay. The next question is, what do these things mean? What do the real and imaginary parts mean? And we will see as we go along that one of the two parts will represent a dissipative effect and the other part will represent a reactive part. Just like in an LCR circuit, you have a resistive part and a reactive part, same thing is going to happen here. Which one is which will depend on the system and the kind of susceptibility, but in the most common examples that you have come across, it is the imaginary part that will represent dissipation and the real part that will represent the reactive part. All response functions, by the way, are of this kind, all of them. For instance, if you look at the refractive index, that when you measure normally in the lab for a piece of glass or something like that, is actually the refractive index at very high frequencies, optical frequencies. On the other hand, at different frequencies you would have different kinds of different values for this refractive index, and along with refraction, along with transmission, there is always absorption, and the real part of the refractive index will represent dispersion and the imaginary part will represent the absorption. Okay. Similarly, for all other susceptibilities, the dielectric constant, for example, the dielectric function is also got a real part and imaginary part, so does the magnetic susceptibility and so on. So the first thing this tells you is that these two go together in this fashion. A little later we will see that this is actually an analytic function of the frequency, and therefore it cannot be purely real, it cannot be purely imaginary, it has got to have both parts. Okay. The next thing we observe is that if this exists for real values of omega, it would certainly exist if instead of this function here you had a damping factor in addition to it. So if this exists for real omega, it also implies that as long as imaginary omega is greater than or equal to 0, chi of omega exists, because if you move in the omega plane, and now let us think of it as a frequency plane, this is the region of real frequencies. If I move up into the complex plane, I just define a function of complex omega by this function here, by this definition here, then that exists, it continues to exist. If the integral exists here when this is an oscillatory function, it certainly exists when omega is somewhere here where it has got a damping factor in addition. So what does that mean? It implies that chi of omega, is an analytic function of omega in the upper half plane. including the real axis by assumption. Okay. What it does in the lower half plane we do not know. This is not going to help you find out as it stands. This representation might break down. In particular, if I go to large negative imaginary values of omega, this will start blowing up and the integral may not exist. In fact, in general it will not exist in this form in the lower half plane except in special cases. Okay. So, all manner of dangerous beasts lurk here, we do not know what they are at the moment, but out here it is a nice analytic function of omega. What can we say from that? Well, the first thing we can say is that over any closed contour C, d omega chi of omega equal to 0, if this C is entirely in the upper half plane, which includes the real axis. Okay. So, as long as that contour does not go down where I do not know anything about what chi of omega is, this is 0 by Cauchy's integral theorem. Okay. It does not say much, it says if I take this omega, if I take that function and integrate over some contour like this, I am going to get 0. Okay. That does not help very much, it does not do very much. Our target is to try and show that this analyticity of omega, of chi of omega, enables you to write the value of chi of omega at any frequency, any real physical frequency, in terms of an integral over all other real frequencies. Okay. And that is called a dispersion relation, and I want to show that that is implied by this analyticity property. To that end, let us do the following. Let us define this function f of omega equal to chi of omega, f of omega prime, let us put a prime here, chi of omega prime over omega prime minus omega, where omega is some fixed real value, some fixed value. And I am going to define it in this fashion, f of omega prime. Now, what are the analytic properties of f of omega prime itself? Well, they depend on the analytic properties of this, which means it is analytic in the upper half plane in omega prime, but there is also a pole at omega prime equal to omega, a simple pole at that point on the real axis. Elsewhere it is completely analytic. So, if I look at this function in the omega prime plane, then at this value omega there is a simple pole, it is a fixed value, some fixed value, and other than that it is completely analytic everywhere on this line except for this pole as well as up there. Okay. So, now let us apply Cauchy's integral formula to this, theorem to this, and take some closed contour C, and I argue that integral f of omega prime d omega prime over C is 0. But of course, this is equal to integral C d omega prime chi of omega prime over omega prime minus omega. Okay. And now let us do the usual trick of blowing this contour up. So, I am going to go as far as I can go, which means I can distort this contour to lie on the real axis because it is analytic there, no problem. I indent this a little bit and then I close it with a semicircle up there in the usual manner. And over that contour too, this integral is 0, identically 0. So, this is some minus r, this is plus r, this point is omega minus some epsilon, that is omega plus some epsilon, which means that an integral from minus r to r d omega prime chi of omega prime over omega prime minus omega. The principal value, because I am going to go to the limit epsilon goes to 0, I am going to leave out this symmetric neighborhood here and then run all the way from minus r to r. That is the principal value, it avoids the singularity out here. I have already explained what the principal value does, okay, plus the contribution from this small semicircle run in this fashion. On that semicircle, omega prime is omega plus epsilon e to the I theta. So on this semicircle, omega prime is omega plus epsilon e to the I theta. So d omega prime equal to epsilon e to the I theta I d theta plus an integral, and over theta it runs from pi to 0 epsilon e to the I theta I d theta function of omega plus epsilon e to the I theta out there divided by omega prime minus omega, and that is equal to epsilon e to the I theta plus the integral of this whole thing over this huge semicircle. So let us call this capital gamma or something like that, okay, plus this d omega prime, etc. That whole thing is equal to 0. Now we play the usual trick. We let r go to infinity. We are going to let epsilon go to 0. This portion has cancelled out already. And then ask what happens to both sides of this equation. Okay. This side is 0 provided chi of omega prime vanishes as mod omega prime goes to infinity in the upper half plane. This term, this semicircle term will also go to 0, and the reason is on this semicircle omega prime is r e to the I theta, and now look at what the integrand looks like. There is a capital R from here, there is a capital R from here, they cancel out, and if this term vanishes, if chi of omega prime goes to 0, no matter how slowly, if that happens, then in the limit as r goes to infinity, that portion goes off to 0. So provided chi of omega prime goes to 0 as mod omega prime goes to infinity in the upper half plane, provided this is true, the limit of this integral plus this is equal to 0, the limit. But what is this equal to? This, if I set epsilon equal to 0, it is just f of omega, and then this integral is I d theta from pi to 0, which is an I pi with a minus sign.
Should it be chi of omega plus?
Not pi, sorry, this chi, yeah, because it is already chi. So provided that is true, we end up with this result which says chi of omega equal to principal value over I pi integral minus infinity to infinity d omega prime chi of omega prime over omega prime minus 1. Okay. There is no sign anywhere of any complex omega now. This is a real frequency, we started with that. This is an integral over all real frequencies. So we made this little excursion into the complex plane, to the upper half plane, came back to the real axis, and this is a connection between functions on the real axis, on the real frequency axis. Okay. This principal value says leave out a symmetric neighborhood of the pole at omega prime equal to omega. Well, all we need to do now is to take real and imaginary parts on both sides, and then you immediately see that the real part of chi of omega equal to, because there is an I pi, so let us move that I upstairs, so this is minus p over pi I times this. I just want to make sure that I have not made a mistake in the sign. So this is minus I pi. I moved it to the right hand side and I got I pi chi. So yeah.
It goes from it goes from pi to 0. So
It goes from pi to 0. So this became a minus I pi.
So then it becomes a plus I. So it's a sign error.
No, the right hand side.
Oh no, it's
No, it's okay. It's okay. Because this is a minus I pi, move it to the right hand side, it's an I pi. I bring the I pi downstairs and it's this. Okay. So what does it say? It says the real part of this is equal to an integral. This has real and imaginary part, so it immediately says p over pi. This p is a symbol, by the way, minus infinity to infinity d omega prime, imaginary part of chi of omega prime over omega prime minus omega, because this would be a real part plus I times imaginary part, and the plus I and minus I give you a plus 1. Okay. And conversely, imaginary part of chi of omega equal to minus p over pi integral minus infinity to infinity d omega prime, real part of chi of omega prime over omega prime minus omega. So these two fellows are coupled to each other in this very interesting way. Okay. If you have two functions of real variables, say f and g, such that f is the integral 1 over pi d omega principal value with a g here, and g is minus this guy here, then f and g are said to be Hilbert transform pair, a Hilbert transform pair. So this is called a Hilbert transform, and real and imaginary parts, real chi and imaginary chi comprise It's an interesting exercise, not a very difficult one, but you have to be a little careful to substitute this in there, and then you should get a delta function which should reproduce this once again. So once I put this in there, you are going to get a double integral, and it turns out that you can do that and it will actually get a delta function. So it actually provides you with another representation for a delta function, incidentally. That is not a altogether trivial exercise, but it is worth trying that out to do this. So it is a little bit like, you recall in Fourier transforms what happened when the kernel of the transform from, we wrote f of t was equal to d omega e to the minus I omega t, and f of omega was dt e to the plus I omega t. So the kernel changed in sign. So this is something similar to that. That is what made sure that you got the Fourier transform of the Fourier transform of the original function itself. That is how this minus function sign does pretty much the same thing. It will ensure that you get a delta function appropriately.